I'm conscious of the time. I'm under strict instructions to wrap at 7:30. So I would like to take any questions from the audience if you have some. There's a hand there, sir. Yes. Is this a question or a statement? You had that air about you.
Is there any evidence or suggestion or philosophy that it can be used for bad, like I'm thinking of perhaps terrorism or warfare or something like that? Is there something that can be used for nanotechnology for, say, novel explosives or chemical agents?
What are you planning? I don't know. Sean might be the man for that. Sean.
This is not my field of expertise. We're not well funded for that sort of research in New Zealand. Probably a good thing. I'm sure there are military applications of nanotechnology. The sort of things you hear about are usually for defence, of course. Such as better body armour and so forth. But as you say, right, there are applications that are quite obviously, you can make a case for the benefit, and also there'll be applications where there'll be quite a downside.
There was a question. Yes, sir.
Can I just add, actually, because I think this is important. The US spends a quarter of its nanotechnology research and development budget, which is about $1.3 or $1.4 billion a year, on military research. Not all of that's defensive. We don't know the exact figures, but we know China, Russia and a bunch of other places also have a big military spending section for their nano R&D. And we had a big review by NATO some years back, I think it was about 2004, 2005, and they were really worried about this because they were worried about a new nano arms race. They were worried about falling into the wrong hands, and they were worried that in a sense, the counterbalances couldn't keep up with the developments of potential rogue groups. So I think it's a good question.
But any technology can be misused. Is that a good reason for putting the brake on it?
I actually think there's a pretty compelling reason for putting the brakes on nano arms development, because I think that the sorts of weaponry that could be developed are quite unique, and in particular the potential for nano bioweaponry I find quite concerning, as did that NATO group. But the big thing that's a concern to me is that we're not actually seeing a discussion about this in international fora. I'm aware of very few, even social scientists, that are tracking the area. And we're starting to have a renewed discussion about controls on nuclear weaponry, for example, but we're not really looking ahead to think about the next generation weaponry. Perhaps we should.
Yes, sir. Can I get back to you, whoever it was we talked over? Yes.
So I've got an answer briefly, and it's DIME, D-I-M-E, which is dense inert metal explosives, and also depleted uranium produces, it's quite clear, a nanoparticle fume, and it's really nasty stuff. The question I have is, I wonder whether Hans would allow that he's been a little bit unclear about the distinction between Mother Nature's use of nanotechnology and ours, and I think it's got to be really clearly stated that we are in a new planet really in terms of what Mother Nature's been doing with DNA and everything else ever since the first small kind of organic chemical. But there is a distinction, isn't there, Hans, between Mother Nature's use of nanomaterials and our foray into it, which is, I think, a little reckless, and I think George and Mike.
I was paid to come here and be controversial and make statements that people could dissociate themselves from. I could make a comment about nanoparticles in food. So milk, we all love milk, and we measured the nanoparticle content of milk, and guess what? It's full of nanoparticles. And why is it full of nanoparticles? Because now we have homogenised milk and not the kind of milk we had when I was at school. And so the process of homogenisation is to spin it all around. The little globules of fat are now suspended in the milk in the form of a nanoparticle. And we could get all worried about that or not. So I don't think there's an easy box. I've said that before. You can't put nanotechnology into one box. And I can sympathise with the argument about silver and socks and cosmetics. I suspect that the nanoparticles have probably been in cosmetics for an awful long time. The same reason that you've got nanoparticles in milk. So is that nature or not nature? I don't think it's a nice tidy line. You've got GM. So the thing about defence is, and we don't make a big fuss about going to the US to deal with the defence industry. I personally don't like it. But the big area in defence is bioterrorism detection. So what they're really concerned about is homeland security, which I personally think is overly paranoid, but that's what they're trying to apply that to mainly, that I can see. So I don't think there's a nice, neat box that you can say, well, this is man-made, therefore it's bad, and then nanotechnology nature. There's a whole spectrum of things.
Perhaps I'll just add one. It was my job to introduce nanotechnology, and perhaps I could have said this, which is that there's a difference perhaps between the nanoparticulates that a lot of the discussion has been about tonight, and nanotechnology. So, for example, Hans's company makes nanotechnology that we'd need to actually detect nanoparticulates in any sort of product or in the atmosphere. So, whereas there's this concern about in particular about the toxicology of nanoparticulates. So, it is useful to keep that in mind, that if we sort of had a knee-jerk reaction and stopped funding nanotechnology, we'd potentially lose the ability to actually detect what's out there in the environment.
And so I think that's a big issue is around the terminology. I think Sean's provided a good example there, but certainly even with the example Hans gave around nanoparticulates in milk, I think one of the key issues around a discerning difference between those types of particles and particles that have been specifically engineered for a specific purpose. So again, certainly in Māori communities again that have had the option to look at nanoparticulates, that's something that is of concern to them, is things that have been engineered for a specific purpose and therefore may not actually behave or may behave in unexpected ways. And I guess this is where some of the information gaps that do exist. As an ecotoxicologist, environmental fate and effects of nanoparticles and particulates is a big issue. There's not a lot known, and we did some research in Canada on titanium dioxide, looking at the effects of that on developing fish. And many people, I've heard people say, well, we've been using titanium dioxide for years, there's been no effects, nothing's rolled over and died. And I bring back to Sally's question that a lot of toxicology now, it is quite sensitive. We're not looking for fish that are floating belly up. We're actually looking for really subtle effects in fish's biologies, which can affect populational change. So whilst you might not see dying fish, there may well be things going on internally that could be causing over the long term, could be causing just as a drastic effect. So I think there is a difference here in terms of the issues around engineered nanoparticles for sure. There's some concerns around those.
Thank you. Yes.
My question is to do with how nanoparticles travel once they're got out of the environment. So titanium dioxide is initially in the cosmetics. How they aggregate once they've gone out of the cosmetics and how they enter the environment. So do you guys know anything like, it's quite hard to get them in solution, I know that. So do you think they stay in the nanoform once they get the product and the soil, perhaps? Or do you think they maintain that the nanotype?
That's one of the questions that people are trying to work through. Because of the lack of ways that you can detect nanoparticles or once they've released into the environment, most of the ways we can do it now is if they're airborne, we can do it with counters, but we can't actually tell the composition. If they are now in the soil or in the water, probably we're going to bore a PhD student stupid with a whole lot of microscopy, because that's the only way they're going to see it. To actually extract these things and find them is very tricky. They will either stay with the solids, so if it turns out, in my carefully chosen German cosmetics, and not meant to have anything nasty in them, that I have nanoparticles and I have a shower tonight before I go to bed, then that will end up in our sewage system. Some of the nanoparticles, depending on what you've got, and we have to think that things like fullerenes, which are made of carbon, which is one of the reasons it's very hard to find them, because I can tell you how much carbon is in something, but I can't necessarily tell you how much of a fullerene is there. Or it's a metallic based. So that will start playing with where it will go and what it will end up. Yes, some of them will stick together. Some of the nanoparticles, especially their surfaces are modified so they don't stick together. Some of them will start dissolving. Sometimes we will have Materials that in the bulk phase, or if they're bigger, we wouldn't expect to dissolve, will start to dissolve. So when they get into, say, some cells and bodies, they are more likely to dissolve than we would expect based on what we know. So it is quite a big unknown, and there's a review that I was reading last night in preparation for today by CSIRO, starting to work through what do we need to know about where some of these things will go. I'm particularly concerned about things that become airborne, because we know a lot about particles and what happens when you inhale them. But we don't know very much about where these will go, whether our sewage treatment plants will hold on to them, and then what will happen once they get out in the environment. Are they going to end up in the sediments? We do know that particles, a lot of nanoparticles, once they're airborne, will behave more like a gas because they're so small, so they can move very long distances. In some cases, with like some of the carbon nanotubes, if they aggregate, that is actually worse. Because once they aggregate, they are now the size of fibres. So if they stick together, sometimes that will make them too big, and if you were breathing them in, the hairs in your nose will push them out. If they stick together to a certain size, then they may actually become entrapped in places in the body that we wouldn't expect. The problem is there are so many different terminologies, there are so many different classifications, that figuring out the ones that are really going to be a problem for us versus the ones that, yes, that's fine, that's a really good thing to use, is going to be quite tricky. And that's simply because the pace at which people are developing these new materials, it's very, very hard for people like myself and my students and Jamie to follow behind, working out what we should say, hey, think about that one again, or yes, that's fine. Now, there are actually precedents, though. In Europe, they have a new law around REACH. It's called the REACH program. What they're wanting to do is stop the amount of animal testing. So they're starting to look at the models and to be able to predict based on shape, based on size, what do things look like? What do we already know? So I think that's somewhere we need to start with. What do we already know? And can we, at the design phase, predict where something may be a problem? Now, this sounds far-fetched, but many of the pesticide companies and increasingly our pharmaceutical companies have people who look at structures, who look at size, who look at shapes of molecules and say, no regulator is ever going to go for that one. We already know that some of these properties will be problematic. And I think we need to teach our students how to do that from the beginning. I believe that being a part of being a practicing scientist is to actually know what you're doing and to think it through. Some people will see that as a very narrow mind.
Let's say we have time for one more question.
I'll just speak up. Right now I deal in the photovoltaic real world of silicon. Can any of the panel advise me on when I can realistically expect to have a nanotype technology panel that I can sell someone in my hand?
Good question. Who would be best to answer that? Sean?
Well, probably me, but I'm not actually sure if I know. I mean, there are nano-based solar cells out there, and I think these things. I might have to call from some of my colleagues in the audience whether there's actually any on the market at the moment. But these things certainly exist, and you know are likely to be with us quite soon.
Is there a global governing body evolving to provide oversight, similar to the IAEA, around nanotechnology?
A global body? Is there? Georgia?
Yeah, the short answer is no. The OECD has tried to play a really dominant role in facilitating discussion, in facilitating a research program, and also in policy debates and about public engagement. But I've got a concern about that because the OECD doesn't represent all the world's governments, clearly. It just represents wealthy governments. And also its key mandate is really to promote economic development. So I don't think it's really the most appropriate global governing body. There have been some efforts through SICOM, which I think I'm going to struggle to remember what the acronym stands for, but I think it's the Strategic Assessment of something Chemicals Management. And it's basically a network of all the world's governments which was set up some years back to try and eliminate toxic chemicals. And it has facilitated a number of dialogues in different continents in the last year or two around nano and around nano policy and governance. But it also, it lacks any kind of real agency over nano. So there is some discussion among civil society groups about whether we in fact do need a new branch, perhaps of the UN, that can perhaps deal with some of these chemical and safety issues, but also do technology assessment. So in a sense, be a place that keeps an eye on emerging technologies and that can share information about that, but also sort of keep an eye on some of the social and the ethical and the economic aspects as well. Now, whether or not there's going to be any receptiveness in the current environment to actually expanding the UN, we'll see. But at the moment, there's not really anything with teeth.
Can I add something?
Yes, Peter.
Let's not forget these manufactured nanomaterials that we're talking about are chemical products, and there are quite a number of international and United Nations chemical management programs. Georgia referred to the SICOM one, which is the, I'll get it wrong myself, but there's also programs run out of the United Nations Environment Program. There's other programs that look at chemicals management and a whole and set up the chemicals management regulatory systems, and the system that we've got in New Zealand with all those assessment for various toxic and ecotoxic properties that I mentioned, that does come out of a United Nations program. There are a number of nano-specific programs that are operating in some of these United Nations bodies, and that includes outreach programs to developing countries.
Thank you. There was another very burning question over there, yes.
Stephen Brown from Soil and Health Association. There's one quick statement too, is that's with the homogenised milk. There's a parallel rise in heart disease as well that followed the nations as they moved into that through the world. The question is really to Peter. It's the regulators that, particularly IRMA, who we have with HASNO through GE, and Peter and I are probably familiar with each other from that, and also with the chemicals there. IRMA has, and I'm correct, I think, Peter, with the market economy, is a major part of the balance on any risk analysis that goes on there. We've just had, as an example, methyl bromide reassessed. There's a very, very high chance, and through Canterbury University here, that's shown a link with motor neurone disease, men dying at ports, men and workers dying in mushroom factories exposed to it. But IRMA has said, because of the big log spike coming, we will make it recapturable for the ozone layer, for the environmental effect, not the human health one, in 10 years' time. Do you think with the EPA that is coming, that it's here, but in July with a bit more clout, with the Minister being able to have direct intervention, we're going to get any more independence and good risk analysis?
I wouldn't say that our risk analysis was in any way deficient at the moment. But no, the answer is that when the EPA does get established, the HASNO element of that will be effectively completely unchanged. It will operate essentially as it does now. But even now, under the HASNO Act, there is the ability for the Minister to call in any application. So the Minister, if he wanted to, could have called in that reassessment of methyl bromide and then run it, according to his agenda. So that is written into the HASNO Act, and that will obviously remain once it gets rolled into the EPA.
All right, I want to thank you all for coming. I want to thank the panel. More questions, I suspect, than answers, but that's all to the good, I think. I was just thinking, I was reading this afternoon a fascinating book called The Emperor of All Maladies. It's a biography of cancer, which has just described, at the point I'm reading it, a couple of things about advances in the treatment of cancer which seemed pertinent to this discussion. Two stories which can be used to argue both ways, in effect. Pierre and Marie Curie's discovery of radium in 1902 was a huge step forward. Radiation therapy catapulted cancer medicine into the atomic age, and radiation could obliterate certain forms of cancer. But it also produced cancer, as Marie Curie and many others found out. And in a sense, radium seems to me to epitomise the double-edged nature of scientific breakthroughs. I mean, this is life. It's always been so. The other thing that struck me as relevant to our discussion is that the book's description of the collapse of the boundary between the synthetic world and the natural world, something that occupies us today, particularly in nanotechnology. But this first collapse was in the 1820s, when a German scientist boiled an inorganic salt and created urea, which is typically produced by the kidneys. And this is what the book says, that a chemical produced by natural organisms could be derived so easily in a flask, threatened to overturn the entire conception of living organisms, organic and inorganic chemicals. Wohler was his name. Wohler proved were interchangeable. And if the chemicals of life could be synthesized in a laboratory, would they work on living systems? Could a molecule concocted in a flask affect the inner workings of a biological organism? I mean, that's certainly something that Bill Joy might have been worried about were he to have been alive at that point instead of more recently. And it strikes me that this is a precursor with strong similarities to the prospect of nanotechnology used in medicine or in other areas. As one says weekly at the end of a discussion when one doesn't know what else to say, food for thought. I want to thank the panel, Sean Hendy, Sally Gore, Hans van der Voorn, Peter Dawson, Jamie Altaria, and Georgia Miller. Thank you.